Okay, we're back on 0.6 trigonometry, and we're dealing with trigonometric graphs. And if you recall, we talked about how the vertical shrink or stretch is affected by the A, and then it can also cause it, if it's negative, to be a reflection about the x-axis. The vertical shift is D. The horizontal stretch or shrink is B, also reflecting about the y-axis at times, if it's negative. And then the horizontal shift is C. So with this, we have an example: determine the period, domain, range, and then draw the graph of negative sine 4x plus pi. So the first thing I do is I'm writing the form of the equation here, and then I'm showing you the different components. But if you notice, I factored a 4 out of the expression 4x plus pi. It's kind of weird factoring if you're not really used to it. But remember that factoring, if you're going to pull out a factor of 4, you're dividing each term in that expression by 4. Okay, so the first thing we get is the period. The period is 2 pi over b. The b value is 4. So it's 2 pi over 4, so that's going to be then pi over 2. Pi over 2 there. So the period is pi over 2. If you look at the graph, I've drawn the graph already. I tend to draw graphs that illustrate the period, because then I can work in quarter cycles, if you will. So what I would do is I would take this to pi over 8 and then 3 pi over 8 here. Okay, and I work with the mins and maxes of a sine graph and then go from max to min, through those all three of those. So I might go from the 0 to the max to the 0 to the min and bounce back and forth that way. Okay, well, you'll see how we do that. Okay, and then I'm just going to put this one in here, negative pi over 8. Okay, so the domain is still going to be negative infinity to infinity, and we're closing that up. Okay, we can put any x value we want in there. Here's our x-axis. And then the range is going to be governed by the amplitude, which is negative 2, because there's no shifting. I have the d is equal to 0. Over to the right in pink, I have a d value, and it turns out to be 0. There's no shifting up and down. So then the range is going to go from negative 2 to 2, and we have hard brackets on both sides of that expression. Now that range comes from the amplitude. If we take the absolute value of negative 2, we get 2. So our function, sometimes people, I don't know that I can do that here. Let's do it in white. So these are going to be, well, that's not white. So if I go from up here, that's not an asymptote. No. It's just showing you that my function is going to be trapped between those values, negative 2 and 2. So now, the first thing I'm going to do is I'm going to graph the function. Let's see if I can do it in purple as a dashed line. I'm going to graph y is equal to 2 sine 4x, because the 4 has the period in it. If I put 0 in it, it should make sense that it's going to be 2 times 0, right? And so this is going to be a dashed line. And if I end after the period is pi over 2, by the time I get to pi over 2, I should be back at 0 then. So we know that the sine is an increasing function, so I'm going to go up to a quarter cycle to 2, down to the equilibrium, down to the minimum value. And I know this isn't your first rodeo, so I'm not going to belabor this too much, just to kind of get you back into this. Okay, there is y is equal to 2 sine 4x. Then I'm going to flip it. I'm going to work with negative 2 sine 4x. And I'm also going to do a dashed line with that one. And so with that, my y values become negative. So these zeros are still the same. So instead of being up at 2, I'm at negative 2. Instead of being at negative 2, I'm at positive 2. So you can kind of see the graph here. And I'll draw that as a dashed line there. Okay. Now the only thing left to do is to take it to the final equation, where I've got a translation. I've got a translation that's going to take the graph pi over 4 units to the left when we add pi over 4. So let's take that to a blue graph then. And so here we go. Instead of being at the origin, I'm going to move pi over 4 units to the left. So I'm going to put a point there. And then I'm going to go down at the point that's at pi over 8. I'm going to move that over pi over 4 units. That's 2 tick marks. So you can kind of get this in your head with how far you have to move a graph if you just count the number of tick marks. So instead of being at 3 pi over 8, 2, that point is going to move over here and here. Now let's draw one period to see what this graph looks like. So we're going to go like this. Okay, and like that. Okay, so that'll give us one period of the graph of our final graph of y is equal to -2 sine 4x plus pi over 4. So, and then completing the graph, you can see that we kind of run into the other one. And there's our final graph in blue. Put arrows on the end because the pattern continues, okay? So there I've drawn 1.5 cycles or 1.5 periods of the graph. And I was going to shift these over so you'd see how they work, but I think we're probably pretty good on that. I'm going to slide that down here. It's kind of interesting when you do it step by step that way. So if you need to go back and review how I got those different graphs, then go ahead and do that. Just want to say briefly something about the inverse trigonometric functions. So none of these 6 basic trigonometric functions graphed on slides 15 and 16 is one-to-one. These functions do not have inverses. So if you go back and you look at some of the functions, these are the sine and the cosine, if we're graphing them. Going back here, these are one-to-one. These are, the sine graph is not one-to-one, neither is the cosine, because if you draw, they don't pass the horizontal line test. Okay, I'll let it go at that. In each case, the domain can be restricted to produce a new function that does have an inverse. The domain and ranges of the inverse of the trigonometric function become part of their definition. So you can kind of look. Here you have the first one is the cosine graph, cosine inverse. So you can switch the x and y's where you see that you have the point 1, 0. 0, 1 is on the graph of cosine. And if you have the point -1 pi, pi -1 is on the graph of cosine. So just switching. Here's the sine inverse, the tan inverse. And see you only have one cycle, if you will, inverted. Okay, here's the secant. Okay, here's the cosecant, and so the cotangent finally. And what we've done with the regular trig functions is we limit their domain so that their inverses will be functions. And we'll talk more about those then. So inverse trig functions. So I left 2 graphs here for you to graph the sine and the cosine. I'm going to skip over those, but make sure that you can put these values in from 0 to 2 pi and get the parent functions. And then for the tangent. Okay, so making sure that you get those graphs in here. But we're going to jump up to an inverse trigonometric function. So remember that if you want to find the measure of sine inverse of -1/2 in degrees, it's kind of easier to think because your angle is in degrees. It's easier to think about pi over 2, which is 3.14 something over 2 as about 1.5. It makes a whole lot more sense. But if we get decimals like that, it's sometimes not clear. Oh, but if we get 90 degrees, it's like in our thinking, it works better. In this particular case, when you see this notation, theta, I'm going to say, remember that theta is equal to sine inverse of -1/2 because inverse trig functions are angles. They produce angles as outputs, where your input's the ratio. This input is the ratio. And then the output, this is the output, is going to be an angle. Okay? So when I see this, I go, oh, that's the angle whose sine is -1/2. So remember, sine is equal to -1/2. Sine is negative in the 4th quadrant and 3rd quadrant, right? Now, if we're talking about only the principal values, we're only dealing with the 4th quadrant here. But sometimes we like to include from 0 to 2 pi, so we'll talk about that briefly. So if I'm looking at the angle and I say, well, this is my theta is equal to the sine inverse, then I want to think about what sine theta is. Well, sine theta is -1/2 then, so that's going to be my y over my r value, if you will. So I'm going to make that -1, 2, and it looks kind of familiar at that point because you're going, oh yeah, that's right, it's square root of 3, right? You got to have a point on the terminal side here that's square root of 3, -1, right? The x value, then the y value. So we recognize that angle, the smallest side is opposite the smallest angle, so we know that theta is equal to 30 degrees, but it's not 30 degrees. It's -30. It's going in a clockwise fashion, right? So it's either 30 degrees, and if we're going from 0 to 2 pi, say we're going to discuss this. This is the answer for the principal value. If you put that in a calculator, that's what you're going to get. The principal value for the inverse trig. But if you put it in a calculator, you could test these other ones. You could say if you're going from 0 to 2 pi, and we'll include 2 pi there. So then you could say, well, the angles, theta, that would make this true could be, if you're thinking about from 0 to 2 pi, it's not going to be in the first quadrant or the second quadrant. So if you look at this, then third quadrant, that's going to be 30 degrees more here, right, than 180. So that's going to be 210. Okay, and you're looking, 0 to 360. I guess I should have said, 0 to 360. So these are degrees, right? And 210, and then the other one would be 30 degrees less than 360, which would be 330 degrees. So just if you're thinking about in degrees going from 0 to 2 pi, but if you use the principal value, it's going to be this one. Okay, so I just thought I'd let you know, sometimes you're getting these negative answers. If you're going to do anything in your calculator, I would probably set it in degree mode if you're trying to get an angle when you're first getting used to it. Okay, so that's all I have in this, like, dealing with inverse functions. You have 3 keys. Remember, you have y is equal to, actually the buttons, sine x, cosine x, and then you have tangent on your calculators, not the y equal. But you have those 3. So when you're looking at graphing these, I did skip over this. So I want to go back very briefly to the graphs. If you're graphing trig functions, sine, cosecant, and tangent, they're odd functions. No, that's not what I wanted. If you're going to graph the secant and the cosecant, I know I had it here, but here it goes. So for these 3, when you graph them, you're going to have to put them in as the reciprocal function when you go back to graphing those, because you don't have a key for the secant, cosecant, and cotangent. So the same thing is true when you're going to do the inverse. You don't have the second inverse keys, second sine, second cosine. So you're going to have to rewrite your expressions, and we'll go over that in the next lesson. But I have one more video for you, so I want to get part 3 to you as soon as possible. And you guys have a good day. Again, this is trigonometry, trigonometric functions. So have a great day. I'll see you when I see you.